Hey, in this series, we'll go through the Nim Language Manual. It's written by the author of the language, Andreas Rumpf, along with Zachary Karajov. It's a bit dense, especially in the beginning, but I'm sure we can all learn something from it. This and the following videos are basically a collection of snippets from my live streams. I hope it will save you a lot of time and make the content a little bit more approachable. So if you'll see some chat messages in the top left corner, feel free to ignore them. Nim code specifies a computation that acts on a memory consisting of components called locations. A variable is basically a name for a location. Each variable and location is of a certain type. The variable's type is called static type. The location's type is called a dynamic type. The variable's type is called static type because this is what we define, right? We define a variable. Well, the location's type is called dynamic type because location is allocated, memory is allocated during runtime. And the same memory could have different types of data in it throughout the life of the program. Okay. If the static type is not the same as the dynamic type, it is a supertype or subtype of the dynamic type. Wow, this is a mouthful. If the static type is not the same as the dynamic type, it is a supertype or subtype of the dynamic type. Okay, so basically we're saying that if the data in memory is of type A, the static type, if it's not exactly the same, it's either a subtype of that thing, so whatever inherits from it, or a supertype, which is the opposite. Interesting. I guess they're somewhat compatible, and that's what matters here. Interesting. An identifier is a symbol declared as a name for a variable, type, procedure, etc. Okay, so that's a very important word here. Identifier, we'll see it everywhere. Okay, so the identifier can be either a variable name, it could be a type, could be a name of a procedure. Whatever we name is basically an identifier. The region of the program over which a declaration applies is called the scope of the declaration. Okay, I think we're all familiar with the scope. Scopes can be nested. Yes, because you can have a, procedure within a procedure. You can have a loop within a loop. Each has its own little bit smaller scope that is considering only I presume, specific set of identifiers within it. The meaning of an identifier is determined by the smallest enclosing scope in which the identifier is declared, unless overloading resolution rules suggest otherwise. Exactly. So the whole idea is that if we have, a procedure within the procedure, that nested procedure is the one responsible that, can add more, can do something else within its own scope that won't be affecting the one outside of it. So you basically don't have things like the var keyword in JavaScript that would affect something outside of scope. Interesting. An expression specifies a computation that produces a value or location. Okay. So an expression specifies a computation that produces either value or location. So location, I guess, in this case, is a pointer somewhere in memory, or value, which is the actual value that we can apply somewhere. Okay, so I guess this is like an intro into value types and reference types. Maybe that's what it means. Expressions that produce locations are called L values. An L value can denote either a location or the value the location contains, depending on the context. Okay, so I guess that L value basically is our reference type. Something that can be pointed to, and we either, depending on context, we operate on that pointer as a reference or on its actual value. All right. A Nim program consists of one or more text source files containing Nim code. Makes sense. It is processed by a Nim compiler into an executable. The nature of this executable depends on the compiler implementation. It may, for example, be a native binary or JavaScript source code. Okay? That's the whole idea about Nim having multiple backends. In a typical Nim program, most of the code is compiled into the executable. However, some code may be executed at compile time. That's very important. This can include constant expressions, macro definitions, and Nim procedures used by macro definitions. Most of the Nim language is supported at compile time, but there are some restrictions. See restrictions on compile time execution for details. We use the term runtime to cover both compile time execution and code execution in the executable. Oh, okay. Yeah, because during compilation, it kind of has its small version of a runtime. And that's the idea here, I presume. The compiler parses Nim source code into an internal data source called the abstract syntax tree, AST. Okay, so if you deal with macros in Nim, you'll be dealing directly with the AST. Then, before executing the code or compiling it into the executable, it transforms the AST through semantic analysis. This adds semantic information such as expression types, identifier meanings, and in some cases, expression values. An error detected during semantic analysis is called a static error. Exactly. So if you have, your Nim suggest, that's what Nim suggest does. It turns things into abstract syntax tree and tries to compile it, like right before compilation. It does all those checks. And if there's an error, like, oh, the types here are matching or whatever, it throws out an error without actually compiling the whole code. So errors described in this manual are static errors when not otherwise specified. Okay, so by default, it's all static here. Okay. A panic is an error that the implementation detects and reports at runtime. The method for reporting such errors is via raising exceptions or dying with a fatal error. That's funny. However, the implementation provides a means to disable these runtime checks. See the section pragmas for details. Okay, so we have some kind of control here. Whether a panic results in an exception or in a fatal error is implementation specific. Okay, thus the following program is invalid. Guess this one. Even though the code purports to catch the index defect from an out-of-bounds array access, the compiler may instead choose to allow the program to die with a fatal error. So we have an array from 0 to 1, and we specify index of 5. We try to access the index of 5 and put n in there. And if there's a problem of like index defect, echo invalid index. So, we're trying to do something, right? And if there's an error of index defect, you might think that it's gonna just say it, but the compiler may instead choose to allow the program to die with a fatal error, so it's just not gonna throw an exception, it's just gonna die. Interesting. The current implementation allows switching between these different behaviors via -- panics on or off. Oh, that's cool. So you can actually decide if you do something crazy like, index out of bounds, if you want to be able to catch that error and just in case correct it, which would be, I guess, very, very interesting when it comes to, high resiliency apps or whatever, that, you just catch the errors and, at least everything else doesn't die, or it's absolutely necessary that your program is 100% correct and, So I can see that you could develop with panics on, and then when you're sure that everything works and you have a million ways to catch those just in case errors, then you could in production have panics off and just super strong logging so that you can make sure that if something goes wrong, it's not the end of the world. Your production won't die. It's just some specific request maybe will be denied or error. Interesting. When panics are turned on, the program dies with panic. If they are turned off, the runtime errors are turned into exceptions. The benefit of panics on is that it produces smaller binary code and the compiler has more freedom to optimize the code. Oh, that makes sense. So there are less checks, probably. Yeah, less checks, and we can optimize things a little bit more because we're not putting possible errors everywhere. An unchecked runtime error is an error that is not guaranteed to be detected and can cause the subsequent behavior of the computation to be arbitrary. Unchecked runtime errors cannot occur if only saved language features are used and if no runtime checks are disabled. Oh, so the moment we start using pointers and other unsafe features, then those unchecked runtime errors can occur. Other than that, we guarantee that no such things will happen. Okay. A constant expression is an expression whose value can be computed during a semantic analysis of the code in which it appears. It is never an L value and never has side effects. Constant expressions are not limited to the capabilities of semantic analysis, such as constant folding. They can use all Nim language features that are supported for compile time execution. Okay, since constant expressions can be used as an input to semantic analysis, such as for defining array bounds, this flexibility requires a compiler to interleave semantic analysis and compile time code execution. Okay, so basically what it means that we can have constant expressions, as in some code that will execute during compile time and result with concrete value. And that means that with this whole interleave semantic analysis and compile time code execution, what that means is that, you can have basically constant expressions depending on other constant expressions and, use it throughout, and the compiler will basically figure out how to get and compile the whole thing. Okay, that's great. We saw this in action, it's absolutely awesome. It is mostly accurate to picture semantic analysis proceeding top to bottom and left to right in the source code, with compile time code execution interleaved when necessary to compute values that are required for subsequent semantic analysis. We will see much later in this document that macro invocation not only requires this interleaving, but also creates a situation where semantic analysis does not entirely proceed top to bottom and left to right. Yeah, you can do crazy stuff with macros. All right. Hey, that was the first chapter. That wasn't bad. It was, definitions, that's for sure. So we know about L value, we know about constant expressions, various errors. We learned about turning off panics, which is interesting, and all that stuff. Cool.